In this lecture, we are going to look at the memory maps of the PIC16F877. We are going to begin by looking at the data RAM. The data RAM address space is 512 file registers. Each file register is 8 bits wide or is a byte wide. The address space is partitioned into 4 banks. Each bank has 128 file registers. Bank 0 is addresses 00H to 7FH. Bank 1 is addresses 80H to FFH. Bank 2 is addresses 100H to 17FH. Bank 3 is addresses 180H to 1FFH. The lowest 32 file registers in banks 0 and 1, and the lowest 16 file registers in banks 2 and 3 are SFRs. SFRs are used to control, operate, hold status information, or hold data for a particular functionality or peripheral on the microcontroller. Some of the file registers are mirrored in more than one bank. For example, the file register PCL at address 02H in bank 0 is also found in banks 1, 2, and 3. The rest of the file registers are general purpose registers. General purpose registers or GPRs are used for any use as per the choice of the programmer. The SFRs can be grouped into core SFRs and peripheral SFRs. Core SFRs are those SFRs that control the basic operation of the microcontroller. Peripheral SFRs are those SFRs that control the operation of particular peripherals on the microcontroller. The highest 16 bytes in bank 0, that is addresses 70H to 7FH, are mirrored in banks 1, 2, and 3. This address range is referred to as the working space. It is the set of file registers that are accessible from any of the 4 banks. We are now going to look at the functions of the core SFRs. Generally, each core SFR is made up of a number of bits, and each bit is responsible for a particular function. The status special function register is found at addresses 3H, 83H, 103H, and 183H. This means that this SFR is reflected in all the 4 banks. The status SFR is made up of the bits as indicated on the illustration. There is the carry flag, the half carry flag, and the 0 flag. These indicate the corresponding results in arithmetic and logic operations. Then we have register bank select bits. These are the bits that are used to indicate the register bank that is to be addressed at any given particular moment. RP0 and RP1 are the register bank select bits that are used to select register banks when using direct addressing. The combination of those bits will select the banks as either bank 0, bank 1, bank 2, or bank 3 as according to the combinations that are shown on the illustration. IRP is the register bank selected bit that is used for indirect addressing of the file registers. The state of IRP selects between banks 0 and 1 or banks 2 and 3 depending on its state as indicated on the illustration. The PD bit is the power down bit. It is a bit that is used to power down the microcontroller. The T0 is a timeout bit, a bit that indicates that there was a timeout. Option range is found in banks 1 and 3. It is made up of bits as indicated on the illustration. RBPU is the bit that is used to enable or disable weak pull-up resistances on port B. We'll discuss more on these pull-up resistances when we get to the topic that discusses about ports. Int edge is a bit that is used to select between the rising edge and the falling edge as the edge that triggers response to an external interrupt. T0CS is the bit that is used to select the source of timer 0 as either external pulses or internally generated pulses. This effectively selects the timer as either a counter or a timer. T0SE is the bit that is used to select between the rising edge and the falling edge as the edge on which pulses are counted when timer 0 is operating as a counter. PSA is a bit that is used to assign the prescaler between timer 0 and the watchdog timer. PS0 to PS2 are the bits that are used to select the prescale ratio. We shall discuss more about the prescaler when we get to the topic that discusses about timers. But in general, a prescaler is used to divide the frequencies that are being counted by a timer. The INTCON SFR found in all the 4 banks is a collection of interrupt flags and interrupt enable bits for those interrupts that are core to the PIC16F877. RBIF is the interrupt flag for port B on change interrupt. INTF is the interrupt flag for external interrupts. Timer 0IF is the interrupt flag for timer 0 on timeout interrupt. RBIE is the interrupt enable bit for port B on change interrupt. Int E is the interrupt enable bit for external interrupts. Timer 0IE is the interrupt enable bit for timer 0 on timeout interrupt. The PEIE bit is an interrupt enable bit that enables or disables all interrupts that are associated with peripherals on the microcontroller. So this means if we disable, if we make that bit to be a 0, the PIC will not respond to any of the peripheral interrupts. The GIE is the global interrupt enable bit. It is used to disable or enable responds to all the interrupts on the microcontroller. So if we reset it to 0, then the PIC is not going to respond to any of the interrupts. PIE1 and PIE2 are SFRs that are a collection of interrupt enable bits for interrupts associated with the various peripherals that are found on the PIC16F877. We will discuss more about each interrupt when we get to discuss about the respective peripherals. PIR1 and PIR2 are SFRs that contain the corresponding interrupt flags for the respective interrupts associated with the various peripherals that are found on the PIC16F877. PCON contains 2 bits. These are the brownout reset bit and the power on reset bit. These bits indicate the respective type of reset that would have occurred. BOR indicates that there was a brownout reset. POR will indicate that there was a power on reset. The file registers that make up the data RAM are addressed using 9-bit addresses. The file registers can be accessed using either direct addressing or indirect addressing. In direct addressing, the instruction supplies the 7 lowest bits. The remaining 2 most significant bits are supplied from the register bank select bits RP0 and RP1. Together, the register bank select bits and the 7 bits from the instruction form a 9-bit address that identifies the particular file register in question. This means that before we access a particular register, we need to set the register bank select bits RP0 and RP1 so as to indicate the bank in which that register is located. For indirect addressing, the pointer register supplies the lowest 8 bits of the address. The 9th bit is supplied from the register bank select bit IRP. So similarly, together, the bit IRP and the bits supplied by the pointer register will give a 9-bit address to identify the required file register. So similarly, IRP needs to be set accordingly before a particular file register is accessed using indirect addressing. The only file register that can be used as a pointer register is the register FSR. This register is located at address 04H. So in other words, FSR is a special function register that is used as a pointer for indirect addressing. There is another special function register used in indirect addressing. This register is INDF. It is at address 00. In essence, this register is not a physical register, but it is just an address that is used to effect the indirect addressing. We shall see how it does that in a later section. The program counter for the PIC16F877 is 13 bits wide. This width corresponds to the 8K program memory address space. The program counter is held in two SFRs. These SFRs are PCL and PIC. PCL is found at address 02H and is mirrored at addresses 82H, 102H, and 182H. PIC is found at address 0AH and is mirrored in addresses 8AH, 10AH, and 18AH. This means that these two SFRs are found in all the four banks. PCL provides the lowest 8 bits of the program counter. PIC provides the higher 5 bits of the program counter. By design, branching instructions supply 11-bit address. This means that out of the required 13 bits for the whole memory, only 11 bits are supplied by the branching instruction. Therefore, branching instructions will only allow branching within a 2K address space. If branches go across a 2K boundary, there is a need to set bits 12 and 13 of the program counter in software. So in other words, before we perform a branch instruction, we need to set the bits 12 and 13 in software so as to indicate the 2K address space that we intend to branch to. This corresponds to setting bits 4 and 3 in the special function register PIC. Let's now look at the PIC16F877 instructions. PIC16F877 instructions can be put into 4 groups depending on the types of operations performed by the instructions. We have instructions that carry out operations on bytes. The kinds of operations that can be carried out on bytes are data transfer, arithmetic operations, logic operations, and rotates. For instructions that operate on one operand, the operand is held either in the working register or in a file register. For instructions that operate on two operands, one of the operands is held in the working register and the other operand can be held either in a file register or can be an immediate value. The results of the operations can be either stored in the working register or in a file register as is relevant to the instruction. Then we have a group of instructions that perform operations on individual bits. The kinds of operations that can be carried out on individual bits are setting a bit and clearing a bit in a file register. The result is stored back in the file register in question. Then we have a group of instructions that carry out branching and call operations. So under this, we have the go to instruction. This causes program execution to branch to a particular instruction in the program. We've got the bit test and skip instruction. This instruction, depending on the results of this test, that is, depending on whether a bit is set or a bit is cleared, is according to the instruction, it causes the next instruction to be skipped or not. So if the next instruction is skipped, it means execution will go to an instruction that follows the next instruction on the program. Then under that group, we also have got the call and return instructions. Then In the group for CPU control instructions, we have instructions that control the operation of the PIC itself. These include instructions like clearing the watchdog timer and making the PIC to go into a sleep mode. Microchip company developed an assembly language for use with the PIC microcontrollers. The table shows the 35 instructions for the PIC16F877 written using the Microchip assembly language. So we can see the opcode mnemonics. We also see the format in which the operands are written. On the operands, F represents the address of a file register. The address is a value in the range 0 to 127. Remember, instructions only supply the 7 lowest bits of the address of a file register. The other bits are supplied from the register bank select bits. D represents the destination of the result. If D is 0, the result is stored in the working register. If D is 1, the result is stored in file register F. B represents the bit number. It's a number in the range 0 to 7 corresponding to the position of the bit. 0 is the least significant bit position and 7 is the most significant bit position. B is used in those instructions that operate on individual bits in a file register, and it indicates which particular bit the instruction is going to operate on. K represents either an 8-bit immediate value to be operated on by an instruction or 11-bit address to which a branching instruction causes the PIC to branch to. The second column indicates the descriptions of the respective instructions. The third column indicates the number of machine cycles that each instruction takes to execute. The fourth column indicates the format in which the corresponding machine codes for the instructions are in. The fifth column indicates the flags that are affected by the instruction. In the Microchip assembly language, hexadecimal numbers are indicated by the 0x prefix. For example, 0x56, 0xC8. Binary numbers are indicated by the prefix 0b, example 0b10110011. Decimal numbers, you have no prefix. So if a number is just written as is, the Microchip assembler will interpret it as a decimal number. For example, if you just write 43 or 125, these numbers are going to be interpreted as decimal numbers. We have here a number of instructions to illustrate how instructions are written using the Microchip assembly language. Instruction number 1 means add the value in the working register to value in the file register at address decimal 27, then store the result in the file register at address 27 decimal. So the one after the comma indicates that the destination is a file register. Instruction number 3 means load the value, the hexadecimal 7E, into the working register. Instruction number 5, PSF0x77,5, means set bit 5 on file register at address hexadecimal 77. So the value after the comma is the bit position. The value before the comma is the address of the file register. Instruction number 7, it means exclusive OR the value in the working register with the immediate value hexadecimal 5A. The result in this case is stored in the working register. Instruction number 8, call 0x2C5 means call a subroutine that starts at address hexadecimal 2C5. Let's look at some important microchip assembly code snippets. The first snippet is a snippet that can be used to effect a conditional jump depending on the state of a flag. So in this case, we're using the example conditional jump to routine 1, to label routine 1 when the carry is cleared. So the first instruction is a conditional skip instruction. It skips the second instruction if the bit being tested in the first instruction is set. So the bit being tested in the first instruction is the carry flag, and it is located in the status register. So you can notice that where we put the file register, we've put in the name of the register that contains the carry flag. So SFRs can be represented in instructions using their names. The names will be changed into the address, in the corresponding address of the SFR. Likewise, the bit positions, the name of the bit can be used to specify the bit position. So in this case, C will be going to be resolved into the bit position for that bit. So if the carry flag is set, the go-to instruction is going to be skipped. So therefore, there's not going to be any conditional, any branching. If the carry flag is cleared, then the second instruction is not skipped, resulting in branching to the label routine 1. The second code snippet is the one used for looping. In this case, we are decrementing a file register until it goes to 0. So the first instruction causes this decrementing, and if the file is not yet 0, if the file gets to 0, the second instruction is going to be skipped, so which means we'll go out of the loop. But if the register has not yet reduced to 0, the second instruction is not skipped, resulting in branching back to the label loop. So which means a number of iterations of the loop can be performed, and this number of iterations depends on the number that is original in the file register at address 51. We go into some exercise. Attempt all questions from chapter 2 tutorial questions and submit solutions for questions 1B, 1C, 1F, 3, 4A, 4D, 4G, and 4H via the Google Classroom platform.